Hi everyone, I am Supratha Bhaumik. Welcome to the live session for the course Fluid Dynamics for Astrophysics. This is week 7. Let us start by um, revising the material covered in this week's lectures. So, to recall, we were studying spherically symmetric transonic solutions, uh, steady flows for accretion or emission of fluid uh, onto a compact solid object. So we started out with the mass conservation equation and the Euler equation with body forces. So we wrote down the mass conservation equation, and the Euler equation looked like this. And since we are dealing with steady flows, we ignored del del T's. And since spherically symmetric, we are dealing with spherically symmetric flows, we ignored everything except del del R, all variations except radial variations. Um, All right. And combining these two equations, combining mass and momentum conservation equations, led to this equation. And the general solutions are of six types. Of the first one, the second one, solutions denoted by such lines, solutions denoted by such lines, the fifth solution, and the sixth solution. And to recap, solutions of the type 5 and 6 were physical because at a given R, you have two solutions for the Mach number. That's unphysical. So we dispose of 5 and 6. And solutions of the type 3 and 4 are not transonic because this line denotes the sonic point, and these solutions don't take you from this region to this region. So 3 and 4 are not transonic solutions. What are transonic solutions that are physical are basically solutions of the type 1 and 2. Amongst these, the solution of type 2 gives you emission. For example, solar wind. Why? Because it's like the fluid. If this is the compact object at r equals 0, then the fluid starts from rest near the compact object and it goes on to attain velocity after being emitted from the compact object. And solutions of this type are accretion type. Why? Because fluid will start off from really far away from the object, and this fluid will move closer to the object, retaining velocity, and finally get accreted. Okay. All right. So, so solar wind. To recap, solar wind was initially predicted because of really high temperatures of solar corona. So it was predicted that the plasma in the solar corona has such high temperatures that gravity couldn't possibly stabilize this extremely high gas pressures. So it has to be ejected from the sun in the form of a solar wind. And all the planets in the solar system are sort of immersed in this solar wind. And the way Earth deals with the solar wind is it deflects the charged particles. Why? Because charged particles will interact with magnetic fields. How will they interact with magnetic fields? Well, the charged particles will follow the magnetic field lines. And in this way, Earth, since it has its own magnetic field, will deflect uh, the charged particles around and beyond the Earth. Now, what are the factors that determine the motion of these charged particles around wave field lines? What parameters decide how closely these charged particles uh, bind around and gyrate the magnetic field lines? Well, just to recap, we look at the force exerted by the magnetic field lines on the charged particles. Uh, so for that, you have to look at the component of velocity which is perpendicular to the magnetic field. Q being the charge of the particle, B being the magnetic field line. And this will be equals to mv squared by r. This is the centrifugal force because of which this particle will gyrate, this charged particle will gyrate. And this gives you the radius of gyration. So how closely this particle gyrates depends on the velocity, on the charge of the particle, and on the strength of the magnetic field. All right. Uh, so just a few fun facts. How far do these solar winds travel? Uh, well, they will travel until the sheer ram pressure of this solar wind can push through the interstellar pressure. Okay, and after some point, of course, the interstellar pressure uh, will be large enough such that the solar wind can't push through this, and that's when the heliopause occurs. Okay, and what signals this heliopause? Once you cross the heliopause, you will see a sudden drop in temperature. You will detect B field direction changes, and there'll be sudden increase in galactic cosmic rays. You will suddenly start detecting more galactic cosmic rays, right? So this was what was detected by this Voyager 1 in September 2012. Voyager said that NASA declared that in late August 2012, Voyager had actually crossed the heliopause because it had seen these signatures, and this heliopause occurred at around 120 AU. For reference, the distance between Sun and Pluto is 39 AU. So you can see that the planets are well within the heliopause. So all of these planets in our solar system are well immersed in these solar winds. All right. So in our treatment of solar winds or these accretion and emission, once again we considered spherically symmetric, steady transonic solutions. Okay, but solar winds are technically not spherically symmetric. This was also shown in the lectures where the velocities of fluid uh, as a function of theta around the sun was displayed, and it was shown that well, they are not spherically symmetric. Um, Also, these solar winds carry B field lines, magnetic field lines. That was not incorporated in our treatment of the solar winds. And these solar winds are also accelerated. So the flow solutions are not really steady, even though we treated them as steady. All right. But we don't touch these, we currently don't deal with these complications. Uh, okay, what's more? What's more is that the solar winds have been detected to be faster and thinner, the density is lesser than what we predict from isothermal assumptions, right? So that can be taken care of by using some other gamma. Without going into details, this is just to mention, just to remind you what are the assumptions we worked with, and they are technically not valid in the real life solar winds. All right. Uh, Two other things that were recently taken care of or studied very recently, and not studied very recently, but they recent papers that were also cited in the lectures came out, is taking care of the fact that sun rotates and taking care of the fact that fluid doesn't really start from rest near the plasma that is ejected from solar corona. It doesn't really start from rest. Okay, so how can we hope to take these into account, or how were they taken into account in these recent works? Once again, details will not be provided. It's you can go through these papers, but these are details, and we'll just review the main results of these papers. So, how do you incorporate the rotation of sun and non-zero initial velocity? So these solutions of spherically symmetric, steady, transonic, etc., these solutions are Parker solutions. Does this fluid movement affect the sunspots? Um, so emission of solar wind is different from sunspots as far as I know. Uh, there might be sunspots are accompanied with uh, uh, really intense temperatures and things like magnetic reconnections and so on. I think they're I'll have to check how they are related with solar winds, but yeah, I'll get back to you on this. All right. Um, okay. Um, thank you. Thanks. Okay. So these are the solutions that did not incorporate rotation of sun and assumed zero initial velocity. But how do we hope to incorporate these two in our solutions? We write that the actual solutions are these Parker solutions. On top of that, we write small perturbations, rho and v, and we are still working with steady solutions. Only now we just write this parameter, exponential of I omega t. That gives you the time evolution of these of the density and the velocity of these of this fluid. Um, and we will say that these are allowed solutions, or we can hope to incorporate these two effects by writing this if these solutions are stable, if these perturbations are stable. What does it mean? It means that if omega was imaginary, then depending on the sign of omega, if you plug these solutions back into your equations, mass conservation and momentum conservation, and you see that omega turns out to be imaginary, then what happens is this exponential of minus I omega t will either be exponential of minus some minus k or exponential of k. This is a damped solution. This is a growing solution. So exponential of minus k sort of tells you that these perturbations die down, and exponential of k tells you that these perturbations keep growing. So you're no longer in the perturbative limit. These perturbations keep growing. But that's not quite true. We want to keep the perturbations that result from incorporating these two effects to be small. We don't want them to grow indefinitely or just damp down and decay to zero. Okay. So it had been seen that if you plug these back in, you will find that omega is real, indicating that these solutions are stable. So this is a successful way of incorporating these two effects. Okay. Similarly, if you plug these two in the equation taking care of rotation of sun, because then you would have an extra force, you would see once again that omega is real, indicating that the solutions are stable. That's it. All right. Now in solar wind, we since the sun is a really massive object, you would expect that on top of solar wind, you should also expect some sort of accretion onto the sun, right? Because sun is a massive object, it would of course attract objects onto it. Now, one would like to compare the energy scales that are released in, let's say, nuclear fusions versus the energies that are that can be potentially released uh, as a result of accretion. Okay, so let's compare the energy scales that are released in these two processes, and let's see which one would overwhelm uh, the other. Now, just take this, we are not working out the steps, uh, but the energy released per hydrogen atom in nuclear fusions is around 10 power minus 2 mpc square. Okay, the typical scales is around 10 power minus 2 mpc square, mp being the mass of ionized hydrogen. Now, the work done, this is the gravitational potential energy. What's the gravitational potential energy? Simply the work done to bring an object of mass m from infinity to the surface of a compact massive object, the mass of the compact object being m star and the radius being r star. So you're bringing the object of mass m from infinity to a distance of r star. You're bringing it to the surface. So you're essentially accreting the body of mass m onto the compact massive object. This work done is the gravitational potential energy, which is this. Okay. Now, if you define something called the Schwarzschild radius, and the way to look at a Schwarzschild radius is this: every massive object, you can calculate the Schwarzschild radius for every massive object, and that's related to the mass of the object via this relation. And the way to look at a Schwarzschild radius would be that if this entire mass were contained in this radius, that object would be a black hole. Okay, that's how you look at the Schwarzschild. That's how you interpret the Schwarzschild radius. So if you re-express E accretion, the energy of this accretion, in terms of R S, you will see that it's this. Okay. Now, if the sun is of course not a black hole, if you were indeed dealing with a black hole, then of course that's the definition of the black hole, that R star has to be much less than R Schwarzschild. The radius of the black hole has to be much less than R Schwarzschild for that object. That's why it's a black hole. In that case, Rs by R star would be much, much greater than 1, which means that the E accretion would be much, much greater than mc square. Now, if this object being accreted were a proton, then the energy for accreting one proton would be much, much greater than mc square. Whereas the energy released in burning one proton in burning in nuclear fusion is 10 power minus 2 times mpc square. So we can clearly see that accretion is much more efficient in releasing energy. It will release greater energy than nuclear fusion processes. Okay, but of course, the sun is not a black hole. If you calculate the Schwarzschild radius of the sun, it will turn out to be 3 kilometers. We know the mass of the sun, so we can calculate Schwarzschild radius for the sun. It's 3 kilometers, whereas the radius of the sun is much, much larger than that. It's around 10 power 6 kilometers. So we see that Rs by R star is m Schwarz. M star is the mass of the object whose Schwarzschild radius you want to compute. Okay, so we can see that the radius of the sun is clearly, sun is not a black hole, and you will see that this factor is much, much less than 1. It's clearly less than 10 power minus 2. So we can see that accretion is not as efficient as nuclear fusions for the sun. Okay, all right. Any questions up until now?
My question is, you said that for a black hole, this Schwarzschild radius will be much larger than the radius of the actual radius of the object. But what about for a neutron star then? Because a neutron star also accretes.
For any massive object to be a black hole, black hole, you can colloquially, black hole is looked upon as what? It's looked upon as something whose gravitational pull nothing can escape. So from that argument, any mass, any massive object, if any amount of mass m star is contained within a scale Rs, then that object is a black hole.
No, I'm talking about a neutron star. Then what will happen for a neutron star?
You take the mass of the neutron star and you calculate Rs, and you will see that it's not a black hole. Why? Because Schwarzschild radius of neutron star this is lesser than the radius of, let's say,
Okay.
it will be less than Rs as far as I know. See, the point is, you take any object, you calculate its Schwarzschild radius. Just because you're calculating Schwarzschild radius of an object does not mean it has to be a black hole. Even all objects, any massive object, you can compute the Schwarzschild radius. If you can contain that mass within that length scale, then it becomes a black hole. Okay, that's how you look at the Schwarzschild radius.
Okay.
Okay,
Hmm.
all right. All right, so let us move on to Eddington luminosity uh, and accretion. All right, so what puts this limit on luminosity of the maximum luminosity of any object that is accreting matter? Well, let's first take a luminous compact object, and let's say it's accreting matter. So there's infalling matter, and since that this object is luminous, it's radiating photons. This compact object is luminous, it's radiating photons. This infalling matter, this radiation will pass through this medium of infalling matter, right? And it will experience, this infalling matter will experience an outward force because of this radiation. This outward force is equals to this quantity, where sigma t was called the Thomson scattering cross section, L was the luminosity, R was the radial distance at which this infalling matter is, and so on. Now, why is that? Luminosity is the energy radiated per unit time. Luminosity of an object is the energy radiated per unit time, which will basically be equals to the integration of F radiation times ds. This is integrated over the surface of the compact object. That F radiation is the energy flux, of course, per unit time. So if a compact object is radiating an amount of energy dE over a surface dA in time dt, then F rad for that compact object will be dE divided by dA dt. And you will compute the luminosity by integrating this over the surface of the compact object. All right. Now, the radiation force, which is minus grad P, this radiation force is equals to rho kappa by C times F radiation, where kappa is something called the opacity. What is opacity? Opacity is the fraction of the energy that is absorbed by the medium through which radiation is passing. Okay, and the medium in this case is this infalling matter per unit density. Hence, you multiply this opacity by rho and multiply this with the total um radiation, and that gives you what amount of total momentum flux, energy flux or momentum flux goes towards the infalling matter, and that is what will uh, that is exactly what is pushing this infalling matter out. That is exactly what is exerting a radial force outwards for this infalling matter.
What does this capital P stand for here?
This,
Capital P.
this,
Yes, yes.
that's the pressure, the gradient of pressure being the
Okay.
radiation force.
Hmm.
Okay.
And what is this Thomson's cross section? Because this was not explained in the lecture. The name
Thomson's,
was.
okay, so just look at it as the, so scattering cross sections, right? If you look
Yes.
at particle-particle interactions, the scattering cross section encapsulates the strength of this interaction, right? So this is nothing but the scattering cross section of, let's say, an electron and a photon.
Okay.
Hmm. All right. So this F rad, which is L divided by this square of sorry, F rad, which is the luminosity divided by the surface area of this compact object, that is L by 4 pi r square, multiplied to rho kappa by C, gives you this radiation force, which is basically this. Rho kappa is when you compute this, you will see that it's just sigma t. That is why this is the outward radial force. These are details that are not terribly important, but it's good to know where this is coming from. Okay. Okay, so this is the outward radial force acting on the infalling matter because of the radiation. This is the radiation force, radiation pressure on the infalling matter acting outwards, pushing it out. Now, what is stabilizing this or what is fighting against this to support for the accretion to continue? Uh, the inward gravitational force of this compact object, right? The gravitational force is this. Now, for equilibrium to be achieved, this inward force, this inward pulling force has to balance the outward pushing force of the radiation. If you balance these two, you will get an expression in L, which is the Eddington luminosity. Okay. So if L were any larger than L Eddington, then the radiation force, radiation pressure will overwhelm the gravitational force, and that will result in this infalling matter to be pushed out. So the gas will be blown away. That's the significance of Eddington luminosity. Any questions? Okay. Now, how can we relate this to any sort of limit on the accretion rate? Now, let's say matter is being accreted onto this compact object of mass m, and the rate of change of this mass of this compact object with time is m dot, and this is because of the accreting matter. So let's say m dot is the accretion rate because of the infalling matter. That's how with time the mass of the compact object increases. Now, let us assume by some mechanism, and we do not bother too much about the exact mechanism by which this happens, but let's say some fraction of this rest mass energy, rest mass of the accreted matter is converted to radiation. So this outward radial force that was acting on the infalling matter, let's say this radiation is being provided by the accreted matter. Some process is going on in the accretion disk, because of which this accreted matter, some portion of it, some epsilon fraction of it, is being converted to radiation. Okay, then the luminosity is what? It's basically this. M dot c square is the mc square would be the uh, rest mass of the accreted matter. And since we're talking about the energy per unit time, the energy radiated away per unit time, this is epsilon m dot c square. Epsilon fraction of the accreted rest mass is being converted to radiation and radiated out, contributing to the luminosity of the compact object. Okay, if that is the case, if you can relate the luminosity to the accretion rate, then you can see that at L equals L Eddington, if you accrete more and more, then that matter will be blown away because you're increasing the radiation pressure. And if radiation pressure starts overwhelming the gravitational pull, then that matter will be blown away. So you can't accrete at a faster rate than a certain amount. There's a limit to the accretion rate. Okay, so if I shouldn't say more, I should say if matter is accreted faster, then it will simply be blown away because there's a limit to the luminosity. Okay, all right. Uh, so there was something also called the accretion radius that was introduced in the lectures, and uh, you used this parameter, and a few statements were concluded that, and without proof, that in the case of spherically symmetric accretion, transonic flows will give you the largest accretion rates and so on. So what is this accretion radius? The sense of this accretion, the way you look at this accretion radius is, well, if you took a test particle which was supposed to be accreted onto this compact object, and let's say the velocity of this test particle was v infinity, at infinity, far away from the compact object, then the kinetic energy of the particle is simply half mv infinity square. The radius at which this total kinetic energy of this particle, as it is accreted onto the compact, as it comes closer and closer and is getting accreted onto the compact object, the radius at which this entire kinetic energy is converted to potential energy, that radial distance you call the accretion radius, and that makes sense. Does that make sense? Just ask if you have any questions.
Can you just repeat the definition of the accretion radius?
Right. So let's consider a test particle far away from the compact object, effectively at infinity from the compact object. Let's say it has a velocity v infinity. Now it is under the influence, let's say the kinetic energy is what? Half m v infinity square. Now let's say this test particle comes under the influence of the gravitational force of this compact object. What happens is it starts getting accreted, it starts getting pulled to the compact object. At a radius of Ra, let's say that this kinetic energy of this particle is completely converted to potential energy. That means that it's completely under the influence of this compact object. You equate this two and you find this radial distance, and that is the radial distance at which your accretion disks start getting formed.
Okay.
Make sense?
Yes, yes.
Okay. That's how you look at accretion radius. That's your physical sense of the accretion radius for now. All right. Okay. So in this entire process of emission and accretion, let's say we know the flow properties, the let's say the velocity or the pressure, the density, the temperature at a certain radial distance from the compact object. Uh, and we want to relate it to these flow properties at some other radial distance. How do we do that? Let's start from Bernoulli's equation. Now in the lectures, this term was replaced by a squared by gamma minus 1. Why is this true? Let's derive this. A is nothing but the sound speed. So a square, a square is basically c square. That's the notation. A square, which is del p del rho. Now p is proportional to rho to the power of gamma. Let's call this proportionality constant as k. So what do we have? A square is del rho of this thing. Now k is just a constant, it's pulled out. Del rho acting on rho to the power of gamma will give you this. But this is nothing but k gamma rho to the power of gamma by rho. Now k times rho to the power of gamma you write as p. So this thing is nothing but gamma p by rho. So dp is nothing but k gamma rho to the power of gamma minus 1 d rho. So you substitute this over here and you get this. You perform this integral and you get this. Once again, you use k times rho to the power of gamma to write p and you get a rho 1 by rho. And this, and what is gamma p by rho? That's a square. So you basically get this. This is this. Okay. So we substitute the second term with a square by gamma minus 1 and right. So let's substitute a square by gamma minus 1, right? Now, let's say we are considering cold gas at infinity, at a infinite distance from the compact object. Let's say the gas is cold. So U is basically 0. So, and since this is a constant, we can relate this quantity for the gas, this quantity of the gas at any radial distance. It will just be a constant. So at infinity, this is 0 because I just said that the velocity of the gas at infinity is 0. So this term is 0. And since phi is gm by r, this term also dies at r tending to infinity. So all you're left with is a squared by gamma minus 1. So we write a infinity, which is, remember, the sound speed at infinite distance from the compact object, in the sound speed in the uh, gas medium, a infinity squared divided by gamma minus 1. And on the right hand side, we equate this entire thing to at a rate to a radial distance at the sonic point rs. Now at sonic point, u is equals to cs. That's the definition of sonic point. Mark is 1, which is u by cs or u by a. So u square is nothing but a square, a where a at r equals rs, rs being the sonic point. So this first term is ar square by 2. The second term is ar square by gamma minus 1, which is this term. The last term is minus gm by rs. All right. Just to remind you, rs is basically this. So we substitute this over here to get this right hand side. What have we done? We have related the sound speeds in the gas medium, which is infalling, accreting onto the uh, compact object at infinity and at sonic point. This is how they are related. Okay. Further solving this right hand side and cancelling terms, you get this relation. Now notice one thing, gamma is always greater than 1. You can argue from thermodynamic point of view that gamma is always greater than 1. What does this tell you? This tells you that ARS, the sound speed at sonic point, is greater than A infinity. Because then 5 minus 3 gamma is less than 2, So 2 by 5 minus 3 gamma will be greater than 1. So ARS is greater than A infinity. All right. Okay. Now, uh, recall how rho was related to A. How was rho related to A? We just saw that A square was related to rho by this, right? And K is just a proportionality constant. It will be the same no matter where you're taking, whether at RS or at R equals infinity. So once you take this, uh, once you substitute this over here, you get powers of rho, gamma minus 1 powers of rho, because this is how the sound speed and density are related. Okay, gamma cancels from both sides once you substitute for density in ARS and A infinity, and you get this relation for the density at these two radial distances from the compact object. Okay, this gives you this relation. This was not proved in the lectures. Okay, once again you see that if gamma has to be greater than 1, then rho RS has to be greater than rho infinity. Okay, because 1 by gamma minus 1 has to be greater than 1, and this quantity is greater than 1. So what does this tell you? This this statement was given without proof, but you can see why it's true. We've just seen why it's true. That if you consider radial distances less than much less than RB, where RB is defined by this. This is remember if you remember this is another form of an accretion radius. This has similar structure. 2gm by A infinity square, where A infinity is sort of the velocity of the fluid of the particle that is being accreted at infinity. This is another sense of accretion radius. So if you're considering radial distances from the compact object, which is much less than RB, once you cross these scales, you will see a significant increase in pressure and sound speed. This you can see. Since we've already seen that the sound speeds increases, the sound speed at ARS is much larger than the sound speeds at infinity. And RS is once again less than RB. Why? Because RB is this and RS was GM star by 2A RS square. So clearly if ARS is greater than A infinity, then RS has to be less than RB. Right? Alright. One more thing that was mentioned without proof, just for your knowledge, is that the velocity of the fluid will go as 1 by r square for radial distances much greater than this accretion radius, but it will change behavior to 1 by root over r for radial distances less than rb. This is sufficient to know. You don't need to know the proof of this. Okay. So the point is the flow properties are quite different once you, if you're considering radial distances much larger than the accretion radius as opposed to radial distances. If you're looking at radial distances much smaller than the or lesser than the accretion radius. Okay. Uh, Another point that was mentioned was that when you're dealing with these accretion solutions, right? Then if you remember, the accretion solutions went like this. So this was Mach squared. This was radial distances. This is, let's say, Mach equals 1. So this points, this line denotes the line which if you cross, you have a transonic flow. So this was the accretion sort of solutions. And if you see this region, in this region, the fluid is actually supersonic. So once the fluid crosses certain point, it becomes supersonic. And we studied shocks. We saw that when a fluid attains supersonic velocities, shocks can develop in the fluid. Okay. Now, if shock fronts develop, what the shock fronts do to the supersonic flow is they convert this supersonic flow to subsonic. But to retain supersonic flow in this region, we then once again need to go from subsonic to supersonic. And if you want that to happen smoothly, we need another sort of transonic flow in this region of R. How does that happen? That only happens if we have a Mach equals 1 region in this R. And for that to happen, we need a radial dependence on gamma. Remember, we did consider different values of sound speed. We did get different values of sound speed just in the previous slide, but we held gamma fixed. In this entire region, we are holding gamma fixed, and that's what's giving us this flow. If we want another sonic point in this region, we already have a sonic point here. If we want a sonic point in this region, we have to vary gamma, because gamma p by rho, which is Cs square, otherwise is not going to suddenly become u by u square by c square is not going to become 1 suddenly. Then Cs has to change, which means gamma has to change. And in this region, that means that gamma has to have radial dependence. I hope this point was clear from the lectures. All right. Now, if you remember, when binary systems were being discussed, when let's say the binary system of a black hole near a star was being discussed, you saw this nice illustration where um, content from the star, matter from the star was being sucked into the black hole via this Lagrange point L1, right? Uh, and the professor made a statement that since this matter that is infalling into the black hole has non-zero angular momentum, that's why the accretion around the black hole cannot have spherical symmetry. The accretion, the flow of this fluid cannot be spherically symmetric. It takes a disk symmetry. Now the question is, why can't infalling matter with non-zero angular momentum follow spherically symmetric flows, accrete in a spherically symmetric manner? Let's see why. Actually, spherical symmetry in a system implies conserved angular momentum, and I'll show you why. If the infalling matter has angular momentum, then this system of black hole plus whatever infalling matter has a changing angular momentum. The angular momentum of this system changes with time. If that happens, you cannot have spherical symmetry. Why is that true? Spherical symmetry would mean you have central forces. Whatever potential is there, it only depends on R. That's what spherical symmetry means. You don't have a theta phi dependence. So the potential has just radial dependence. So the force calculated will be central. What does that mean? That it means that it's radially directed, the forces. Okay? Forces are given by gradient of wave. Okay? All right. Now the angular momentum of the system,
Can
which
you
is
explain the spherical symmetry part again? I
all
could not
right.
hear properly.
So what does spherical symmetry mean? The potential that acts on the system that governs the dynamics of the system, can it have theta phi dependence if it is spherically symmetric? If I wrote a potential which was, let's say, I don't know, some a sine theta, some appropriate dimensions of energy, then it has a sine theta dependence. Does the system have spherical symmetry? If you compute the force with this potential, you compute the gradient of this potential, you will see that it has some theta cap directed forces. Now, if the force has a theta component, now just to remind you in case you're confused, let me remind you of the radial coordinates. This is, let's say, r. This direction is theta. This is x, y, z, the Cartesian coordinates. This direction is theta. Or if you want theta to be polar coordinate, uh, whatever angle the vector makes with z axis is theta, and this angle, whatever angle the projection of the vector in the xy plane makes is phi. Okay. Now, if the force is along theta direction, can it have spherical symmetry? A particle at, let's say, theta equals 0 will experience a different force as opposed to a particle at theta equals 10 degrees. Can you say that this system has spherical symmetry? Yes or no?
Yes, ma'am, because it's showing some deflection due to the angle deflection, right?
Did you say yes or no?
Yes, ma'am, I said.
No, spherical symmetry essentially means that it does not matter what theta value you are at. Any particle at any theta values, as long as it has the same r, will experience the same. That's what spherical symmetry means. It does not matter if two particles are at different thetas, as long as you have the same r. Spherical symmetry means this. Let's say you draw a sphere of certain r and you consider two particles on this sphere, which have different theta and phi values, but of course the same r, because you're considering them on the surface of a sphere. Okay? Spherical symmetry means it does not matter what theta phi values these particles have. These two particles, as long as they are on the surface of the same or on the surface of the same sphere with the same radius, their dynamics will be the same. That's what spherical symmetry means. Do you understand? Is this fine?
Yes, ma'am, got it.
Okay. All right.
Yes,
Now,
ma'am, thank
when
you.
can this happen? When can this happen? This can only happen if f had some theta phi dependence. If the particle here with some theta phi value experienced some different force as opposed to a particle here with some other theta phi value, can you say that the system has spherical symmetry? Tell me. It's okay. If you still feel like it has, just tell me. I'm happy to clarify. Tell me.
No, it won't have because we're keeping it in the same coordinates, so it won't have, right, ma'am?
I'm keeping it at the same r. I'm keeping it at the same r. If f had theta phi dependence, then it would act differently on a particle at some other theta phi. Do you understand this point? Is this fine?
Yes, and that's what I'm saying. Then it will not have the correspondence. Yes.
I'm sorry, I can't get your point. I don't think I can hear you. That's fine, just tell me. Okay, let me rephrase my question. All right, let's forget about this expression of the force. It would be a no. Okay, cool. Thank you. I hope it's clear. If it is not, tell me. I'm more than happy to repeat this. Okay, just tell me. All right.
No, no, ma'am, it's clear. I guess so.
Okay. Good. Very good. All right. Okay, great. So if that is fine, thanks a lot. It's good to stop and clarify things. So thank you for asking. That's great. All right. So if we have spherical symmetry, then the force is, so these forces are called central forces because they're radially, they act radially from a center. Okay. They don't have theta phi dependencies. They act radially outward or radially inward towards a point, towards the center. That's why it's central force. Okay. All right. Now the angular momentum is r cross p, where r is the position vector of the particle, of the infalling particle, and p is its momentum. Okay. What would L dot be? L dot will simply be you first dot r and you write r dot cross p plus then you dot p. So you have r cross p dot. This is L dot. Okay. But what is r dot? R dot is the velocity of the particle, which is related to the momentum of the particle. How is it related? P is m cross v, m times v. So r dot is just p by m. Also, since p dot is nothing but the force acting on the particle, the rate of change of momentum is the force acting on the particle, And the force we just said is along r cap, and the position of the particle in radial coordinates, the position vector of a particle is always some number times r cap. Okay, this is the position vector in radial coordinates. P dot is also along r. If P dot is along r, what happens to r cross P dot? What happens to r cross P dot? What is this? This is the cross product. Cross product means what? R times P dot times sine theta. Theta being the angle between these two vectors. So what happens to this cross product? Is it zero? Is it oranges? What is it? Zero. Great, great. Thanks. Also, if r dot is along P, thank you, thank you. If r dot is along P, the same thing happens to this. This is also zero. So what is L dot? It's zero. So spherical symmetry in a system implies conserved angular momentum. If the angular momentum is not conserved, you don't have spherical symmetry in a system. Okay? So that's why in falling matter that has non-zero angular momentum cannot form a spherically symmetric accretion disk. It ends up being a disk accretion. The accretion formed is not spherically symmetric. It's not a sphere that it's not an accretion sphere, it's an accretion disk. Okay? All right. This brings us towards the end of the lecture. What happens is that if you're considering Keplerian orbits, then you have no radial velocities of the particle. So if the massive object capital M is what is the difference between what? Shreya, difference between what? Please feel free to unmute yourself. There's just two of you. Accretion disk would mean that the matter that is being accreted around the black hole forms a disk. Accretion sphere is just matter that will form a sphere around the black hole. Okay, that's fine. That's whatever you, if the meet is causing problems, that's absolutely fine. Typing is whatever is fine. Okay. All right. So next thing is we'll try to model the orbits of the particles that are being accreted onto a compact massive object. Uh, and how do we do that? We do that as quasi-Keplerian, where we say that, well, the radial velocities of these particles is very small but non-zero. And v phi, of course, is given by this. And these radial velocities are much smaller than the tangential velocities of these particles around the compact object. Okay, so that's fine. Now we'll solve some sample assignment problems that will help you to solve the quiz, the quiz problems. Mm. Okay, now we have to pick the correct statements where um, these are some relations between post-shock and pre-shock quantities. To remind you, if this was the shock front and the shock front was let's say fluid in this region was moving in region 1 was moving towards the shock front sorry, that's a horrible arrow, towards the shock front, and fluid in region 2 was moving away from the shock front, such that this region 2 is actually the post-shock fluid. So the shock front has already passed through the fluid in region 2. This is actually the shocked fluid, and the fluid in region 1 is actually the pre-shock fluid. So the shock front is yet to pass through this fluid. So this is the unshocked fluid. Okay. Quantities P, Cs, and so on, these are pressure and sound velocities and so on, the speed of sound and so on. Subscript 1 will denote these quantities in region 1, the pre-shocked region, and subscripts 2 will denote these quantities in the post-shock region. And there are some relations. Now, if you remember, and we have to choose which one are the correct relations. Now, if you remember, we derived these jump conditions, and you can either check out the, not either, you have to check out the week 6 live session where this was derived, the pressure, density, and velocity jump conditions. Jump condition meaning how do you relate, what is basically U2 by U1? What are these ratios? These were derived in the previous live session. So I'm not going to rederive them. I'm just going to state these relations once again. So P2 by P1, which is the ratio of the pressure in the post-shock by pre-shock region, is basically given by this, where m is the Mach number in the pre-shock region. Okay, so you will see that the correct option is B. If you take this one to the left-hand side, you will see that the correct option is B, which comes with a gamma plus 1. Okay. Among C and D, you have to pick which one is correct among C and D, you have to look at these two relations. In any of these two equations, let's say you want to substitute this lambda square gamma plus 1 by 2 using this equation. You substitute over here cs1 square plus u1 square gamma minus 1 by 2 minus u2 square gamma minus 1 by 2. We just substituted this using this equation. So this equation you will see is actually this option, which has a u1 square minus u2 square. So the correct options are B and C. Okay, moving on to the next question. We are asked to consider an ideal monoatomic gas. So we know what sort of gas it is, so we already know what the gamma for this gas is. Let's consider a normal shock passing through this gas. The upstream meaning the pre-shock region, the upstream Mach number is 4. So you know what U1 by CS1 is. And the upstream velocity is twice the downstream velocity. What this tells you is U1, which is the upstream velocity, divided by U2 is actually 2. Okay. Now we are asked to find the downstream Mach number. How do we find this? Of course, using jump conditions. So let's see. Let's write this relation, which is CS. Let's write this relation, which relates the sound speed pre-shock, sound speed in the pre-shock region to the sound speed in post-shock region. This is the equation. Now we divide this entire equation by u2 square, by the velocity in the post-shock region, in region 2. So this gives you cs2 square by u2 square, which is the inverse of the Mach square in region 2. So that's m2, 1 by m2 square. For this term, what we do is we have cs1 square by u2 square, which we rewrite as cs1 square by u1 square, u1 square by u2 square. This is nothing but 1 by Mach square in region 1. And we have this term, this ratio. This bracketed term becomes u1 square by u2 square minus 1. Okay. All right. But notice that we have Mach 1, which is 4. So we can substitute this 4 over here, which is 1 by 4 square. And we also know what u1 by u2 is. It is 2. So we write a 2 square over here. And we know what gamma is because we know that it's a ideal monoatomic gas. Okay. So we substitute everything and we get 5 by 4. Inverting and square rooting this, we get the mark in region 2, the downstream Mach number, as 2 by root 5. So the correct answer is D. Okay, next question. We are asked to consider a solar wind type solution, which is spherically symmetric transonic flow. A spherically symmetric transonic flow solar wind type solution that we have studied. We have to pick the correct options. These two options are the same, not the same, they tell different, they're basically opposite of each other. The location of the sonic point is independent of the gas temperature. The location of the sonic point depends on the gas temperature. Which one is true? Any guesses? Any wild guesses? Let it be wrong. Just guess.
It depends on the temperature.
Absolutely. Thank you. Why is that? Because the sonic point is obtained at U by Cs equals 1. Okay. Now, Cs is determined by the gas temperature, right? So, of course, Rs will depend on the gas temperature. So, B is correct. All right. Third option is the dynamical equation remains same under changing the sign of gas velocity. Is this correct? It is indeed correct. This was actually also mentioned in the lecture once. So, the dynamical equation, once you punch the two equations of mass conservation and Euler equation with body forces, you will get this equation. Now, since du dr is accompanied by factors of u, you will see that changing u to minus u introduces minus signs here, but also introduces minus sign here. So nothing really changes. So it remains the same under changing the sign of gas velocity. All right. All right. Fourth question is slightly long and it involves some calculations. So please pay attention. Uh, Consider atmosphere of a spherically symmetric isolated star. This just means that you're not considering binary systems and you have spherical symmetry. Okay, no complications, just an isolated star with a spherically symmetric uh, flow of the atmosphere. Okay, now the steady state momentum equation for the stellar atmosphere is this. So you know what, how the pressure varies with radial distance from the star. This is how it varies. M is the mass of the star and M is the mass of each gas particle. This should probably not be MP, this should just be M. Forget about this P for now. Yeah, there should not be any P. Forget about this P. Okay. Now, you also know what the temperature is as a function of the radial distance from the star. It is given over here. Where T0, R0 are some constants. So at R equals R0, the temperature is T0, which is very clear because this factor becomes 1. So at R equals R0, T equals T0. And it is given to you that at R equals R0, the pressure is P0. It's also given that at R equals infinity, T is 0. This is also clear from this. Now you have to pick the correct option. The options are concerned with the pressure at a given radius. So you have to actually solve for pressure from this. You have to choose whether the pressure goes as this or the pressure goes as this. And the options also ask you whether the pressure goes to 0 at infinite distance from the star. Okay. And this also asks whether the stellar atmosphere is in hydrostatic equilibrium. Okay. All right. So let's do this. We have this equation that tells you how the pressure varies with radial distance. We have to actually solve this to get such an equation or this equation. Okay. So what do? We rewrite dp dr. We take this dr onto the right hand side. So what does this give? This gives me a dP by, I'm so sorry. I'm so sorry. I am stupid. This P is actually the pressure. I got confused. I thought that MP would be the mass of the proton. That's not true. This P is the pressure. So what you do is you bring it to the left-hand side, right? And this gives you Gm by R square dr by kBt. We're just rewriting this equation, okay? But T is not constant with the radial distance from the star. What is T? T goes as this, okay? So we substitute for T over here. We take this equation and substitute for T over here. That gives you T0 R0 to the power 2 by 7, R to the power 2 by 7 divided by R square, which is this. And we have factors of Gm by Kb, which are constant. I'm extremely stupid. Please ignore this P over here. All right. Please don't get confused. I'm so sorry for this. All right. Okay. So this is the equation that we have to solve to get pressure as a function of radial distance. Okay. Uh, okay. So there should be a dr over here and a dr over here. All we do is we rewrite this r to the power 2 by 7 by r square as r to the power of minus 12 by 7. Okay. All right. Now, this will give me a log p, but I have the boundary conditions of this integral. If the radial integral, if the if the radial integrals goes from r0 to r, and this r is what I'm trying to solve the pressure at, I know that the pressure at r0 is p0. So my limits on the integration on pressure will go from p0 to some p of r. Okay. So I have a log of p by p0 on the left hand side, and on the right hand side I get this. This is just integrating this. Okay. All right. Okay. I hope that's clear. What we do is this minus sign gets cancelled and this becomes a 7 by 5. We have these constant factors of G, mm by kb. T0, R0 are constants. And this is just re-expressed as you pull out a factor of R0 to the power of minus 5 by 7, combine it with this to get a R0, and you rewrite this thing as this. So what do we get? We get P is P0 exponential of this entire thing. And if you look at the options, you will see the correct option is D. Okay. All right. Now we have to choose whether B is correct. The pressure goes to 0 at infinite distance from the star. To check that, we check out our solution and see what happens. Now, if you take R to infinity, what happens? Does the pressure go to 0? Okay.
No.
No, that's right. It goes to some finite value. Why? Because this is some P0 e to the power of, let me call this as some constant A, R to the power of minus 5 by 7, exponential of minus A. This is some other constant because there are factors of R0 in this A. So this is basically my pressure. When R goes to infinity, what happens is this term, this entire term does not go to, oh, what did I do? I'm sorry. This entire term does not go to 0. Okay. So this is actually wrong. Next option is interesting. The stellar atmosphere is in hydrostatic equilibrium. Is this correct? Okay, so if you have pressure gradients, can the gas be in hydrostatic equilibrium? What does it mean for the gas to be in hydrostatic equilibrium? That there are no forces acting on the gas. But if dP/dr is non-zero, which it clearly is, then is the gas in hydrostatic equilibrium?
No.
That's correct. That's correct. It's not because there's a pressure gradient acting on it. Okay, is this fine? You know what? I would actually like to reconsider what I just said about this. If this is indeed the solution, then this turns out to be P0 exponential of some constant r to the power of minus 5 by 7 exponential of minus b. Do you agree with this?
Yes.
So if r goes to infinity, what happens to this? This goes
Goes to
to
1.
e to the power of 0, which goes to 1. So this is indeed finite. All right. What we did is correct. Okay. All right. Good, good, good. Okay. So the final problem, consider spherical accretion by a compact astrophysical object. Now we have to pick the correct options. The radiative force due to photons increases with an increase in the Thomson scattering cross section. There's another
True.
similar. That's true. That's true. That is true. Because we just saw that the radiative force was directly proportional to sigma t. So D, which tells you the radiative force decreases with increase in sigma t, is actually false. A is true. All right. Now we have to choose between B and C, which tells you that the Eddington accretion rate per star with the larger radius will be smaller versus larger. Okay, so since the Eddington accretion rate, remember L was some this L Eddington. This was the Eddington accretion rate. Now, if you have a star with larger radius, assuming they are emitting the same amount of flux, right, per unit radius, per unit surface area, which one will have a larger luminosity? The larger star,
Yes.
because this luminosity is this quantity F rat integrated over the surface of the star. So of course, the larger star will radiate more, will be more luminous. So what do we have? The Eddington accretion rate for a star with larger radius will be larger. So correct options are A and C. Okay, so this concludes whatever I wanted to talk about in today's live session. Do you have any questions? If not, you guys are free to leave and I'll stop recording.